The secret to maximizing motor efficiency. Good morning, everyone. In today's competitive industrial landscape, maximizing operational efficiency is paramount. We often focus on motor design or controls, but the true secret to unlocking significant energy savings and performance improvement lies in a fundamental electrical concept: power factor. This presentation will explain what power factor is, why it matters, and how to harness it for your facility's benefit. What is power factor? At its core, power factor, or PF, is an efficiency metric. It's defined as the ratio of real power, the power that actually performs useful work, measured in kilowatts, to the total apparent power supplied by the utility, measured in kVA. Think of it this way: apparent power is the power you pay for, and real power is the power you use. The closer your power factor is to 1.0, or unity, the more efficient your system is. A PF of 0.85 means only 85% of the power you draw is doing productive work. The power triangle. To truly understand PF, we must look at the power triangle. This triangle is a vector representation showing the relationship between the three components of electrical power. 1. Real power, kW. This is the horizontal side, the useful work. 2. Reactive power, kVAR. This is the vertical side, the necessary power that creates magnetic fields in devices like motors. It's essential, but useless for actual work. 3. Apparent power, kVA. This is the hypotenuse, the total power the system needs to supply to handle both real and reactive loads. The larger the reactive power component, the lower the power factor, because that reactive power pushes the total apparent power demand higher. The source of the problem. The primary culprit for low power factor in industrial settings is the ubiquitous induction motor. Induction motors are highly inductive loads. They require a large amount of magnetizing current to establish the spinning magnetic fields needed for operation. This magnetizing current is almost pure reactive power. This continuous draw of reactive power from the utility causes the current wave to lag behind the voltage wave, which is the definition of a lagging power factor, often resulting in site PFs below 0.8. The consequence: system losses. A low power factor has immediate, negative consequences. Since the real power required by the motor is fixed, a decrease in power factor means the motor must draw significantly more current from the line to maintain the same kilowatt output. This excess current flows through all upstream components, conductors, switchgear, and transformers. This leads directly to I²R losses. This wasted energy manifests as heat, stressing your insulation, reducing the life of your equipment, and quite literally sending money up in smoke. Impact on infrastructure. The increased current draw from a poor power factor also strains your entire electrical infrastructure. Firstly, the large reactive current causes an unacceptable voltage drop across the supply lines, reducing the voltage available at the motor terminals. More critically, your transformers and switchgear become clogged with this reactive current. This limits their overall capacity to deliver useful real power to other loads in the facility, potentially forcing you into expensive infrastructure upgrades sooner than necessary. Financial penalties. Beyond the efficiency losses, there is a direct financial consequence. Utilities must size their generation and transmission equipment to handle the total apparent power, the kVA. To compensate for the cost of delivering reactive power, they impose substantial penalties on industrial users who operate below a certain power factor threshold, typically 0.90 or 0.95. Improving your PF is often the fastest way to see a return on investment by eliminating these unnecessary utility charges. Power factor correction, PFC. The good news is that this problem is easily solvable with a well-implemented strategy known as power factor correction, or PFC. Let's look at how this works. How PFC works. Power factor correction relies on the fundamental principle of electrical opposition. Since induction motors are highly inductive, they cause a lagging current. We introduce shunt capacitors into the system, which are inherently capacitive loads and generate a leading current. When connected in parallel with the motor, the capacitor draws a leading reactive current that directly opposes and neutralizes the lagging reactive current of the motor. This means the reactive power loop is completed locally, and the utility only needs to supply the clean, real power required for the work. Benefits of correction. The benefits of correcting your power factor are both immediate and long-term. First, you achieve reduced bills by eliminating those expensive utility penalties. Second, you gain system capacity, freeing up valuable kVA on your transformers and switchgear for future expansion. Finally, the reduced current flow throughout your system results in cooler running temperatures for all components, significantly extending the lifespan and reliability of your entire electrical installation. Impact on apparent power demand. This chart clearly illustrates the dramatic impact of PFC. For a constant 100 kilowatt load, operating with a poor power factor of 0.70 demands 142 kVA from the utility. By implementing correction and improving the power factor to 0.95, the apparent power demand drops sharply to just 105 kVA. Point to the chart. This difference, 37 kVA, is capacity you have immediately recovered and energy you are no longer needlessly dissipating as heat. Questions. Power factor optimization is a low-hanging fruit for industrial efficiency. Thank you for your time. I welcome any questions you may have about assessing your current power factor or implementing a correction strategy tailored to your facility.